Yeah. Okay. Yeah.
Can you see me or just only the slides?
I can see you, sir, but not your face entirely. I mean,
Okay.
yeah, yeah, fine.
Okay. Okay.
Yes, yes. Now it is fine.
Right.
Yeah, good, sir. Good, good. Yeah, I think we will start. Yeah. Richu, are you there?
Yes, sir.
Okay, fine. Yeah, we will start. Okay, so good evening, all of you. So I will start with a quote. In the long run, curiosity-driven research just works better. Real breakthroughs come from people focusing on what they are excited about. So this is a quote from Jeffrey Hinton, as all of you might be knowing, is the pioneer in deep learning and artificial intelligence, and the Turing Award winner, one of the Turing Award winner. In fact, there were 3 persons together shared the Turing Award last year. So with this quote, we start this day. I hope you have enjoyed the previous day session with Dr. Deepak Padmanabhan from UK. Today we have a very special guest, Professor Joemon from Glasgow University, UK. So welcome you, sir. I request Richu Norman to formally introduce today's speaker and pass the mic to the speaker. Over to Richu.
I would like to introduce Dr. Joemon M. Jose, Professor of Information Retrieval at the School of Computing Science, University of Glasgow, UK. He has received PhD from Robert Gordon University, UK, and MS in Software Systems from BITS Pilani, and MSc in Statistics from Cochin University of Science and Technology. He was a visiting research fellow at Carnegie Mellon University, USA. Dr. Joemon has been an active researcher in information retrieval since 1993 and has published over 300 journals and conference articles on information retrieval. His research interest includes recommendation system and deep learning. Dr. Joemon Jose, along with his co-authors, has received Best Paper, Best Student awards at leading conferences including ACM, SIG-IR, CHEER, MMM, and the BCS ECIR. He has supervised as primary supervisors for 20 PhD students and over 20 RAs and postdoctoral researchers. He has chaired several conferences, was one of the program committee chair of the ECIR 2020 and 2017 conferences. Regularly acts as a primary reviewer for AA-STAR conferences and has attracted over £3 million in research funding. He had research collaboration with a number of industrial organizations including BT, Sharp, and Kodak. We welcome you, sir.
Sir, you are mute, sir. Please. Yeah.
It should be okay, right?
Yeah. Yes, sir. Thank you, sir. Yeah.
So I cannot see anybody. I'm going to my presentation mode. It is on another screen, so I cannot see you guys. If there is anything, Santosh or Richu, please warn me. Okay. I can only see my slides now on. Okay.
Yeah. Currently, we are 41 members, sir, listening to you.
Okay. Thank you.
Yeah. Yeah. Right.
Okay. So good evening, all. So my research area is a topic called information retrieval, where we look into how to retrieve information against an information need. That is basically looking at unstructured documents and the retrieval. Right? That kind of technologies underpin search engines. I work in most recently, my team work on recommendation algorithms, recommendation techniques, especially using deep learning techniques. Okay. Now, what is deep learning? In 1997, IBM's Deep Blue, a deep learning-based neural network model, defeated Gary Kasparov. That became a world news. Okay, so it was a Deep Blue was a custom-made hardware as well as the software, and beating a world champion in chess, it was a huge achievement. So I searched for deep learning on the internet, today, and since '97, there are quite large amount of huge amount of progress we made on deep learning. People working in deep learning, many different deep learning models, and also we will get time to time we will get the headlines coming on the achievements of deep learning systems, like recognizing photos, people, things like that. So, what is deep learning? I searched for deep learning on internet, and these are the first two ones that I got. Like, deep learning is a subfield of machine learning, and it is concerned with algorithms inspired by the structure and function of the brain, called artificial neural networks. And it is true, right? So the concept of neural networks, basically idea was to imitate our brain, neurons in our brain, as well as its architecture, so that we can get natural intelligence. Not we can, the software become naturally intelligent. Okay, so that to an extent that is true, right? Another definition is it is a type of machine learning based on artificial neural network in which multiple layers of processing are used to extract progressively higher level features from data, which is again true, which is more like a practical description. Finally, there is a book called Deep Learning from MIT Press 2016. Goodfellow and Benchio, etc., wrote that. It's known as a Bible of Deep Learning. So there, they kind of define deep learning as the study of models that involve a greater amount of composition of either learned representations or learned concepts than traditional machine learning does. Okay, that's one kind of definition from the leaders of the field, and in all sense, all three kind of show some kind of highlight some particular aspects of deep learning approach. Today, in my talk or a tutorial, I'll try to go into the basics of deep learning and try to go into some of the applications we were working on. Okay, let's look at a couple of applications of deep learning. Facial palsy detection. Some of you may aware of what is facial palsy. Facial palsy or a Bell's palsy, as it is known, is a condition that causes sudden weakness in the muscles on one side of the face. I think 6 to 12 months ago, there was a celebrity in Kerala. Basically said he had a palsy and he didn't know what was happening. It is a sudden occurrence, right? It affects around 23 people out of 100,000 people annually. Okay. Now, it is treatable, and the sooner it is treated, the better, right? So, and currently in United Kingdom, ENT surgeons basically they identify the severity of facial palsy by creating a subjective scale, like something known as House-Brackman scale. So, if two doctors use that scale, presumably they all reach a different level of different type of severity prediction. That's why an objective measurement is very important. So we have developed, exploited deep learning models and tried to see how much we could predict. And we could show that on average, 75% of accuracy we can get. Of course, in real life, a facial palsy is measured from a scale from 1 to 6. 1 is normal and 6 being extreme facial palsy states. And however, due to lack of data, uh, we created three groups. Low, I think that is 1 to 2, medium 3 to 4, and high 5 to 6, something like that. So we could get 75% of accuracy in evaluating facial palsy severity. Now, there are quite large amount of social applications we can have on it, like separating stroke from facial palsy, things like that. So, again, the model behind is deep learning. Okay, so we will, and another one is another question is, can we predict a winning horse? Now, horse racing is one of the most archaic sports all around the world, especially in the UK, USA, western side of the world. For horse racing and betting on horse racing is it's a huge activity. So, for example, Kentucky Derby race course recorded 139 million approximately in 2017. So, huge amount of money is transacted there. So, people started looking at, can we predict a winning horse? Similarly, can we predict whether a particular stock is going to increase or decrease? So again, this is an exploration from our side. We looked into the use of deep learning and with a pretty high values, okay, high accuracy. We managed to show the performance on the measurements we were using, like accuracy, precision, recall, etc. So that's a kind of a couple of applications we were using recently. And then at this point, maybe let's look at machine learning versus deep learning. I am assuming most people are familiar with machine learning. In there, we often create, we have data sets or a training data. Then what we will do is we try to extract set of features from this data. Then we use a model. For example, there was a logistic regression model which can recommend a cesarean surgery is appropriate in a given scenario or not. So now in this case, it works on the features extracted from the data, right? The model doesn't look on a person and say this. It looks into the like a age, doctors like a blood pressure, things like that, and doctors' recommendation thing, or doctors' pre-recorded reviews, things like that, and then make up that decision. It also, in this kind of model, work with the cost function so that it try to reduce the error in the cost function. Okay. Finally, there is an optimization algorithm required for learning this. So in the machine learning case, often it is also using linear algebra and solving linear equations because most of the models are linear in machine learning. In deep learning, it's more or less same. However, there are some differences. For example, we sometimes call the architecture of a deep learning architecture because to reflect the high complexity or the variety of components we use for building the deep learning models. Another difference will be we also look into the shape of output units or what kind of functions we are using. In addition, unlike machine learning systems where we try to solve linear equations and train them to then adapt the weights, here we train in a iterative fashion using some kind of gradient-based optimizers. So it is a deep learning, yes, it is a special case of machine learning. It has some set of additional features other than these machine learning models, but in a higher level, they have a similar approach. So now let's look at some of the basics of neural networks. The human brain has around 86 billion neurons. Okay, so this is from PubMed Central from American University Medical Publication. So if you look at the neuron structure on the right, I'm hoping that you can see my mouse movements. So it has a cell. Neuron has a cell body. It also has something called dendrites that receive and process signals from other neurons through something called an axon. Okay, so this is the kind of our understanding about the basic component of the brain unit. Now our idea in neural networks is to try to imitate this model. So an artificial neuron, when we use in our softwares, it looks more like a neuron. Here we do get through the dendrites we are getting in the neurons information. We have our input come to the in our artificial neuron. Each input is weighted with a particular weights. Then a function aggregates them. It somehow aggregates this weighted combination of information. Further, once it is above a threshold, we use an activation function so that we can normalize the output. So, for example, we could use a rectifier linear unit as an activation function. So, which takes the value maximum of it's the input or the above zero maximum zero result. Z is the input in this case. Now, alternatively, we can use a sigmoid function, which is between a 0 and 1. We get an output. So there are many activation functions used. So these are the neurons or the artificial neurons. We are kind of our the structure of the of an artificial neuron. Now, what can we do with this? Fine. If you look at it on a basic form, we are combining a lot of information using its own weights and getting an output. We can use it for classifying information. For example, if you get an image, you want to show it is whether it is a flower or not, binary classification. We could use this kind of architectures. Okay. In reality, what we do is when we have a lot of variables on the input value, it goes through multiple neurons. Okay, in this here the purple one are the input data, and the yellow ones are the neurons. So as you can see, many input data along with the weights are not shown here, right? Is combined in this neuron, and then it is finally combined in an output layer, and we get an output, right? So this is known as something like a feed-forward network. Okay, so here in this network, all the input go through, in this case, 3 neurons, which is combined into an output layer, and we get an output. But what are we doing here? This is known as a feed-forward network. It is a kind of a the classical, most basic form of a neural network. What are we doing here? Let's look at this. We are trying to approximate a function fx. So let's say the output y is a function of all the input variables x. But that f function may be far too complex. It may be a chain of functions, right? First, there is a function f3x, and on to that is applied another function, and applied another function. So you can see that this is a kind of a nonlinear function. Each we have 3 different functions combined together in this artificial feed-forward network and providing an output. Okay. Now, in this case, we are only considering forward network. We are not looking into any backward. We will come to that, right? Now, why do we need these kind of functions? What these functions different from the other functions we know, or like for example, linear regression? Now, let's look at linearly separable space and non-separable space, right? So let's look at the Boolean AND, right? So if you have a Boolean AND operator, when you have 2 inputs, 0 and 1, right? 0 and 0, it's 0. 0 and 1, it is 0. 0 and 1 is 0. And 1 and 1, you get 1 and 1, you get 1, right? So if you look at this, we can draw a line like this, and we can, this space is separable, right? It is linearly separable. We can learn an AND function and draw a line in this space, and we can separate ones and zeros in this. Similarly, if you look at an OR function, again, 0 and 0, 0 or 0, you get 0. 0 or 1, it is 1. 1 and 1 is 1 or 1 is 1. 0 and 1 is 1, right? Again, this space is separable, right? We could find a equation of a line which separate these three outputs from this 0 here. Now, you are familiar with the exclusive OR function, right? Exclusive OR function is basically input two binary values x1 and x2, returns 1 only if one of them equals to 1. Otherwise, it is 0, right? So, I mean 0 and 0 is 0. 1 and 0 or 0 or 1, it is 1. And 1 and 1, it is 0. Now, can we separate it linearly? We cannot draw a line and separate these two spaces here. It is linearly non-separable. Now, the question is, if you were to learn a line to separate this, right, a linear regression model or something, we get equation like this, an output of 0.5, because we cannot separate this space of ones and zeros using a space. So one trick for us to use is to transform this into another space. Okay, so our input is x1 and x2, right? So when you have a data like this, we create two intermediate variables, h1 and h2, h, in which when you have 1 0 and 0 1, you create an h variable 1 0, and when you have x1 1, you create h2 1. Okay, so now h is 0 1 2. Now what will happen is 1 0 1 0 and 0 1, you get 0 and 1 here, right? Now when it is 2 1, that is you get a 0, because hold on a second. Okay, now what we did is, with the initial space, we created into converter into h1 and h2, right? The h2 is you could ignore same as x1, 0 and 1. In h1 you get 0 1 2, that is with transformation for 1 0 point and 0 1, you put that as 1 0, and 1 1 you convert h into 2 1. Now we can create a function on h. Okay, there it is separable, linearly separable. All the zeros is separated from the ones. So here what would happen is, on the x variables, we converted that into an h space, like in a kernel function we use in the machine learning, and then which then further converted into a linearly separable form. We got a complex function. This is exactly what we do in a feed-forward network. The nonlinear function we try to approximate into smaller component functions. Okay. When you have two input x1 and x2, when you have two input x1 and x2, when you have two input x1 and x2, we created an hidden variables or a transformed variables h1, and then which is then pumped through an output layer. Okay, so this is a feed forward network. Input variables go through some hidden information, and then output is. We can learn this function, which is a combination of two simpler functions, which will make a separation of outputs. In our case, exclusive OR function. So here the x1 and x2 are known as input variables, h1 and h2 is known as the hidden variables, and y is the output layer, right? Which can be represented using a much more simpler notation like a x, which you use a weight and then create a hidden layer, and which you use another set of weights and create an output layer. In this output layer, we use something like a sigmoid function to get an output between 0 and 1. In other words, we could convert that into probabilities, right? So there are many forms of activation functions. Sigmoid functions, you get an S-shaped function between 0 and 1. And by changing the beta value, 1 by 1 plus e minus beta a, by changing the beta value, we can get the change the shape of this function, right? So basically, what we are trying to do is transform final node values into probability. Okay. Similarly, there is another function we can use, rectifier linear unit, ReLU function, which is a 0 for anything minimum value, and then it is the other input value is the output. Okay, so you get a function like this. There are many different activation functions we can use. It depends on the application or the scenario. Often one criteria it uses is it should be differentiable. That means that the function differentiation we should be able to use it. We will come to that in a minute. Why differentiation is important. Okay. So to summarize what we discussed so far, feed-forward networks, the basic form of neural networks, has an input layer where we have each node is an input variable, which is then combined by different artificial neurons organized in hidden layers. Okay, in this case we have 2 hidden layers, and then that will be finally aggregated into an output layer, which will then go through an activation function. We get a probability like kind of output. Now, so that means we have an input layer where input nodes data are there. Then one or more layers of hidden units, which is known as hidden layers, and output layer, and then which will pump out the outputs in a most often in terms of probabilities, a probability vector we could call. Okay. Now the number of layers bar the output is the depth of the network, and each size of each layer, hidden layer, is the width of the network. That's a kind of a feed-forward network, right? Now, what we want is we want this network to configure itself. Okay, so either learn from input data or from training examples and generalize for unseen data sets. The question is, once you form a network like this or a variation of this, can this network configure itself to solve a problem? Or how do we train them to learn a nonlinear function to appropriate for the task for which we are learning this? Okay. So let's look at the feed-forward network with one input layer and 2 hidden layers and output. Okay. Now, when you have 3 input variable, you get an output. Maybe it is like a binary classifier. Something is classified as a car or else, right? Or a flower or something else, or an object or a not, right? An output. So when you have a feed-forward network like this, we create an output. Let's say output is OI, and we know from the training data actual value should be YI. So we can find the error YI minus OI. So if it is correct, then the weight should be reasonably okay. If not, we should look at the error. So we use this error, we create an error function like a mean square error, like in a machine learning systems we use. Now we want to reduce that error in future iterations so that these weights can be adapted. How do we do that? So we use some kind of a learning rule. So what we have is we kind of do a small proportion of changes to the weights, and that is based on 3 components. The one is the input, then another one, Ri is the error, and something eta is a learning. So the error is, suppose in this particular case, Ri is error is difference between output and the actual value. If they are same, it is difference is 0. Suppose OI is 1, YI is minus 1. The weight is, the difference is 2. OI is minus 1, YI is 1. Then you get minus 2. Okay. So in this particular example, we expect the output function can take values -1, 0, and 1, right? Now we got an error value. Now what you do is we have input and a learning rate. We then adapt the initial the weights in the neural network with respect to this proportion of this value. Now, so the learning rule has three components: and a learning rate, an error value, and the input. Okay. Now, in real life deep learning systems, we use a small a learning value can be learning rate can be between 0 and 1. We try to use a smaller value of eta, or and then if that value is higher, you can see that functions should look like in each training instance, the loss, that effect on the loss values will be, you know, if you start with a high learning rate, then it won't converge, loss increases. If you use a very low learning rate, you may get a steep change. If you use a high learning rate, you may get it gets saturates. It doesn't go to the minimum. So a good learning rate maybe get a better convergence or reduction of loss value. Okay, so in reality, what we do is we start with 0.01 to 0.1, and then iterate over it and empirically find the right value. Anyway, so we have computed a small change here for the weights. How do we make an effect on the individual weights on the neurons? So this is what we call a technique called back propagation. Okay, this is this back propagation algorithm is exploiting chain rule in calculus. So when you have the output, it reduces the respective weights in the previous from right to left. It reduces the respective weights of each neuron proportionately. So back propagation algorithms evaluate the expression for the derivative of the cos function, and as a product of the derivatives between each layer from right to left, it's going backwards, right? And then with the gradient of the weights between each layer being simple modification of the weights. So that is a backwards propagated error in a proportional way based on the weight each node contribution to the final value. So that way, for each iteration and the second iteration, we compute the output again, we find the error, we use the learning rate, and pump back the error. So through multiple iterations, the errors stabilize, or the loss decreases to a low value, and the weights stabilize. That's where the neural network is trained for a function. Now that process, we don't need to compute the calculation or anything. The software will do it. Use something called a gradient descent learning approach. Okay. So first thing is, we should be using a differentiable activation function, something like a continuous function where we can differentiate with respect to the input variable. And also we have talked about a loss function or a cos function, which measures network's performance errors as a differentiable function of the weights of the earlier layers. Okay, so this is the two criteria we use. So for example, a cos function or the loss function can be mean square error. The input and output and the difference or the input patterns. Then we can change weights to reduce that mean square error, change the weights of the neurons, individual neurons, for it aggregates the input variables. Then in order to create a smaller error. Okay. So that means exploiting the chain rule of calculus, or the difference in variations. We make in each iteration, which we call an epoch. Each iteration we make small changes to the internal or hidden layers, or all the all the weights in the previous layers, so that the loss in the subsequent case, the loss or the cost function is reduced. This is known as this is based on gradient descent learning. So in reality, we use something called a stochastic gradient descent learning, because in deep learning systems, our data set size is very huge. We cannot use the entire data set in one go, which will make the execution very difficult. So in reality, we use a batches of this using a something called a stochastic gradient descent learning algorithm. So if you look at the deep learning, and what is this learning happening, right? There are two types of learning can be. So what is this learning happening? There is a, in deep learning techniques, what we are trying to learn a function in terms of a simpler function in one way, or we are learning complex concepts from simple concepts. But then we are not extracting these simple concepts. Our network learns it and form a complex function through such a combination of different small functions. So our architecture, or the model we call the deep learning architecture, is as an overall that solve a complex nonlinear function. However, internally it is a combination of smaller functions it uses to build a bigger complex function. What we do is we have this iterative training procedure in which we discover these right functions. Now, if you look at this, it can be looked from two different perspectives. One is, when you have a large collection of data, it is what do we call in the collection of data? It is a representation of data. Now, if you use an SVM or a logistic regression model in machine learning, we kind of extract features and feed into it, right? Here, we feed the data. So, when you have feed the data, the important part is to represent that data, right representation of the data. So, deep learning can be used to learn that representation. Or another perspective is the deep learning architecture, the right depth and width of layers which we are discovering, or the model or the architecture what we call. Okay, each layer of the representation or each layer of that architecture can be thought as the state of the computer's memory after executing another set of representations in parallel. So you could see that the state varies from one state to another, reaching a final output, and each state you could see that it is a kind of a memory of the computer's memory of solving that problem at that particular state. So representation learning, right? Unlike machine learning, where we have extracting features, which is a manual process, like age or sex of persons, age, height, weight, blood group, blood pressure, all these variables we are extracting. That is a manual extraction process, right? In the machine learning, here we try to learn that representation from the data. So often our deep learning aims to predict an output. Output like which horse is going to win today's race, right? So this is a mapping from input to output. So the input will be, we will be looking at the horse's performance in the past races, who is the trainer, how good that trainer is, how many races this horse, and what is the age of the horse, things like that. Now we want to predict if it run against 10 other horses, what will be its rank position, whether it will win, if it is in the first position, it will win. If it is not, it won't be winning. Okay. So that's what we are doing, but the same model we use to predict this can be used for learning the representation. So in other words, representation learning can discover a good set of features for simple tasks in minutes or for complex tasks in hours or days. Okay. So deep learning solves representation learning by introducing representation that are expressed in terms of other simple representations. So let me go and introduce something called distributed representation of words, or something called what called the vector representation of words. Okay. So if you are okay.
Professor,
Yeah.
can we pause for some questions if audience has
All right. Hold
so
on.
far?
Yeah. Where can I see? Did they write there?
No, I will read the questions if they or participants, if you have any queries so far, or any clarifications or any kind of reflections, please unmute yourself and ask to the professor, so that we can make sure that you are on the same page. Yeah,
Okay.
yeah. Yeah, since we have interdisciplinary people attending the course, so I just wanted to make sure.
Yes. Yes.
Yeah,
Yeah.
yeah, yeah,
Very important.
yeah, yeah. So please ask questions if you have. Otherwise, we will move ahead. You can type also on the chat box so that I can read it for the professor. Yeah, I think it will be too early.
Okay.
You can proceed, sir. Yeah, please.
Thank you.
Yeah.
Okay. Stop me if there are any questions. I cannot see it, right? I'm only seeing my slides here.
Yeah.
Uh,
Yes, sir. Yes, sir.
yeah.
Yes.
So far, I tried to give a kind of conceptual model of deep learning, the kind of core components, how the structure of artificial neuron, how they are combined into a feed-forward network, and also how we will use back propagation to learn the appropriate ways. And the the important thing is us to learn is we are learning a complex function, and the underlying deep learning architecture encapsulates much smaller functions to form this complex form. Okay. So now, and I talked about representation learning, which is a very important part of deep learning, because it is used in computer vision, it is used in natural language processing, it is used in recommender systems to learn the representation of the data so that the performance of the model can be increased, right? The first of that is something called the word embedding. You must have heard about it, or the word distributed representation of the words. Now, those who are familiar with any information retrieval or natural language concepts, the finding similarity between a two pieces of text, most commonly used approach is something called a cosine similarity, right? You take a two sentences, we form a vector representation and find the similarity between those two vectors using something called a cosine similarity. You know that if two vectors are perpendicular, cos 90 is 0, whereas if they are closer, of course 0 is 1. So if they have the same vector more or less representation, then we get a similarity of 1. Otherwise, we get a similar and we can get a value between 0 and 1. That's the idea there, right? So underlying in this is something called a 1/4 vector representation of each word. That means, suppose we have a vocabulary of 100, we can have 100 vector word, and each vector, 100 vectors, each vector is mostly zeros except in one point where that corresponds to the particular word. Okay, so that means each vector consists zeros in all cells, with the exception of a single one in a cell used uniquely to identify the word. This is known as one hot vector representation. Then in this case, if you have two vectors, you cannot find similarity between words. So what is the similarity between words when you say? Okay, now if you let's look at, if you go and take all the documents written by district administration of Ernakulam, right? So we get Kochi, Alve, Muattura, Kottayam, etc. in it. So there will be some kind of similarity between these terms, right? But you know that the Kochi and Ernakulam may be more closer when you compare to Alve or Muattura, that terms, right? Because they are further away. Greater Cochin area, maybe Ernakulam and Cochin area may be together represented in many documents. So the similarity between them may be higher, right? So the idea here is this. So we want to represent the words as a function of other similar words. So we get a vector representation instead of this one hot vector we talk about here. So this is known as distributed representation, right? So such embedding for words in a continuous space so help us to develop much more powerful language models and give a good generalization. So in some of the downstream slides, I will show you some applications of this, right? Now, in a neural network, when we learn these word representations, okay, they become very powerful in computing similarity between words and sentences or documents. Now, prior to deep learning, there are something like a context counting models like a hyperspace analog to language, HAL or LSA, latent semantic analysis. There, when we have a word co-occurrence information matrix, we can use a computing technique called matrix factorization to separate or identify words semantically similar. So in the neural network, we are looking at a context predicting models. Okay. So for each word, we want to create a vector of words which are similar to this and the proportion or the particular weights for them. Okay. Now the first paper on this by Bunchio et al. It's called a neuropropolistic language model, and I think it's 2003. There they were looking at creating a distribution of word sequences. So here they theoretically, conceptually look at associate each word in the vocabulary a distributed word feature, similar to latent semantic analysis, right? However, here we are discovering that from the collection. So express the joint probability of various words in forming a word, various similar words. So the underlying principle here is, right, words co-occur more often, may have some kind of similarities. So if that is the case, we can express each word as a function, a probabilistic function of other words, more similar words. The proportional probability for each word will be different. So in their work, in this Benchio's work, they looked into creating vector representation of 30 words or 60 or 100 words given as 17,000 vocabulary size. Okay. And in 2013 and 14, I think, this Mikolov and Rong, etc. looked into. Mikolov basically created something called the word-to-vec models. So many people must have heard of this as known as word embedding, or in other words, known as distributed representation of words. It's they introduced efficient techniques to learn high-quality word vectors from huge data sets. So here, unlike matrix factorization techniques, where we have a very complex matrix manipulation techniques, it's much more simpler. Okay, and I will show you the architecture in a minute. So such simpler models can be trained on much more data efficiently, and hence they introduce something called the word-to-vec models or word embedding, and using two different approaches called a continuous bag of words or skip-gram models. Now, the underlying principle or the hypothesis we use is something called a distributional hypothesis. words that co-occur in the same context tend to have same meanings or similar meanings. Okay, so if you take about the Ernakulam district administration, if you look at the documents all coming from their district headquarters or collector's office, you may get that you may get documents which the place names co-occur in that district very often, and that frequency we can look and find similar terms. So idea here, represent each word with a low dimensional vector. Okay, now, and in that representation a word similarity becomes corresponding vector similarity. So if you want to find names of, so if you take the words Kochi and Ernakulam, how similar they are, if you look from a semantic perspective, it may be Kochi and Ernakulam are two different places, but closer compared to other place names we consider in that district or in Kerala. Maybe their similarity may be higher. That similarity we compute based on the vector representation of Kochi as well as vector representation of Ernakulam. Okay. So there are two key ideas here. There are two different models. One is skipgram, another is the bag of words approach. Okay. Now let's look at this. Suppose you have a vocabulary of V words in a collection, and we have all their one-hot representation. Then we can create a word interaction matrix. So we have our vocabulary size is V, and let's create a now V by N connections. That may be N documents on this word as. Okay, so that is our input matrix. Then output matrix, for each word we want to create an output matrix. So what we do is so in between we create a hidden layer. So this is the much more compact layer we are having. Okay, this hidden layer, what they do is, for each word they reduce that into a smaller feature set. From that hidden layer we recreate, for each smaller feature set we try to recreate the words, and finally our output layer is each word vector. However, instead of the one hot vector, this may be a more like a probability vector for each word. So our network is our task is a fictitious task. We want to predict the same word, right? But we use a word interaction matrix, and then we create a hidden layer, and we want to predict the same word. Through that we ignore everything and we go and look into the hidden layer. That is a kind of an embedding layer for us. That's a kind of principle, right? And here what we are doing when we do this, we want to make similar words has a similar closer representation, and dissimilar words has a much more diverse representation. That's the aim of our approach. In other words, when you have an input, like for example, right, we look at the middle word and we want to say whether if we from using the context, the previous two and the forwarding two, can we predict that word? That is a continuous bag of word representation, and they use a window of word to predict the middle word. Another approach, use a word to predict the surrounding words in a window. So when you have the WT, then you are trying to see, can you predict what the word would be, the one position before, or two position before, or one position after, or two position after. Okay, so that's the two approach we want to do that. That is our task here, and using this task, right? So let's consider this example. The cat sat on floor. So the middle word is sat, right? So we assume we don't know sat. So we only look at the cat on floor. The question now is, can we train a model which can predict sat, right? Similarly, so what we do is we are using a 2 by 2 windows in this example. When you have a sentence like the quick brown box jumps over the lazy dog, you start the two windows after we consider quick and brown. So D and quick, D and brown, we can have the samples. And if you move D to the next word, the one word before is D and two further up, so we can have the another three samples. Then when you focus on brown, we have two words before and two words after, and you have another samples. So the co-occurring probabilities we can observe from the data through this windows. Okay. Now, idea is when you look at these words, that words which has a more tendency to co-occur in these windows should be having a more similarity than the words which is not co-occurring. So if you remember the artificial neurons and the hidden layer, the feedforward network, you could look at the one input vector here, right? Suppose this is a one hot vector. I said this one hot vector is majority of them are zeros except for one position, one, and that particular one maybe in this particular case correspond to the word ants, right? So this is our input vector. It goes to multiple neurons. In our particular example, let's say 300 neurons, right? And it aggregates all these zeros and this one. Then it finally goes to an output layer where it produces probabilities. So now what it is creates probabilities for, let's say, 10,000 word positions. Basically, when you say is when you observe the word and, what is the probability of other words happening? That's what we are doing in this particular task. So in our hidden layer, 10,000 words is our vocabulary, and we have 300 neurons. So that means our hidden layers dimensionality is 10,000 by 300. So these neurons represented maybe 300 features. In other words, each of this word is given distributionally represented into 300 other words. Okay, so we get each vector representation for each word with the probabilities for potentially 300 other words. This 300 can be 10, it can be 60, 100, which we decide. So effectively, that what's happening is when you have one hot vector, when you multiply with another weight matrix, what is happening is you are extracting a row forever corresponding to that particular word. And when you learn these weights, right? When you learn these weights through your back propagation mechanism, you are learning the correct representation of that word. Okay, that's exactly the underlying inside the box happening. So now another way of looking at it is how do we compute the probability when you have a word vector for ants with the 300 features, right? 300 dimensions from the 300 neurons, and then we look into the each neuron and the corresponding weight for each word. Okay, because we can multiply, you get a value which outputs the weight for a particular word, in this case car, ants and car. So then it goes through a softmax function to get a value between 0 and 1. Then you get a probability. Okay. Now, if you iterate over, this is our one hot vector for each individual word in the collection. This is our input matrix, which goes to the hidden layer, which has dimension 300, which we prefix. And then it creates an output matrix, and finally the output layer. Each time when you have a one hot vector, we want to find the probability for other words with respect to this word. So that's the output we are getting. When we train a matrix like this, for a task like this, when it iterates over multiple times, a number of times, when the weight stabilize, we get this hidden layer, and that is our word embedding for each of the words. So in this case, for each word, you get around a representation of each word. We get a representation of different features. Okay, different words. Now, if you look at that word representation, how useful are they? So the evaluation, you look into two kinds of categories, semantic and syntactic categories. It asks the question, A is to B or C is to, can you get the correct semantic category or syntactic category corresponding to D, right? So for example, semantic category, London is to UK, United Kingdom, London is the capital of United Kingdom. As Paris is to, then we want the France. Paris is the capital of France. Right? So the question is, when you have something like this, our representation can discover this or not. Alternatively, we can look at the syntactic category. If swim is to swimming, as run is to running. The question is, can we use our representation we learned in our word embedding? Can we predict this? So 10 years ago, roughly 8 years ago, this was become a huge news. We could learn these semantic representations. Effectively, what we do is, in the word analogies, man to woman, right? Man is a male, woman is female, then king should be queen. Whether can we do this? So we use this when you have an equation like this. We use a similarity matrix computation like this. And then the question is, when you do that, can we get the representation of queen or not? So it has shown that this word embedding, we could get the underlying semantic representation to show if man to woman, when you say king, then it will identify queen. Similarly, if you're going to say Paris is to France, Paris is the capital of France, and Berlin is the capital of Germany. So will it system can detect Germany from it, from other names. So it shows the power of word embeddings, word representations or representation learning in solving such a semantic and syntactic categories. So this can be extended instead of having a word, whether we can embed different sentences or paragraphs, etc. Okay, and it improve the performance further. So what is so why this is important? So you may want to ask, pizza and pasta are some Italian dishes, right? So how similar is pizza to pasta? How related is pizza to Italy? If you want to ask these kind of questions to your computer, this word similarity, word embedding, or word distribution of word representations can be exploited. So representing words as vectors allows easy computation of similarity. So it helps us to measure the semantic similarity between words. It works as a powerful input towards for more sophisticated NLP or algorithms like question answering, sentiment computation, etc. So that's a word to vector, but word to vector representation is not considered deep learning because it's kind of shallow learning, only one layer there, right? When you have multiple hidden layers, it is considered deep learning. Otherwise, it is known as shallow learning. So further down the line, you must have heard of something called a BERT, or in other ways, bidirectional encoder representation from transformers. Here, Google created this. They basically created pre-trained models from the unannotated text from the World Wide Web. So, a huge amount of text is available, and training something similar to what we discussed so far, training a distributional representation. They created something called very powerful representation called BERT representation. Okay, so when you have such a representation, the woman went to the store and bought a dash of shoes. It's a pair of shoes. when you could use these representations where then it would say the car will in this context maybe fill 20% of the time, whereas the another word pair may have 80% of the time. So that means you may choose 80% of the time. So this is a kind of paper published in I think it's 2017 or 2018, pre-training what is deep bidirectional transformers for language understanding, and that has made a huge difference to many of the leading NLP NLP tasks. So here, what I am going to discuss now, something called the BERT model, and what I discussed so far, something called word embedding or word-to-word representation. So it is considered these two representations we are going to look. One is called context-free, another is called a contextual model, right? So word-to-word is a context-free word embedding representation. For example, the word bank would have the same context-free representation in two statements, like a bank account, which is something to do with a financial institution, whereas Bank of the River. So that should be getting the same representation, which you may think that now when you talk about Bank of the River, you may prefer to have slightly different representation. Alternatively, you might be able to create a context-based models where it can be differentiate these words. So, for example, in the sentence, I access the bank account. The BERT representation, which I am going to explain now, represents bank using the previous words as well as the words ahead of us. So, in other words, it use something called a bidirectional representation, so that word is represented within the context of its use. Okay, this is possible by the use of another powerful model called transformer, which was created in 2017 by Vaswani et al. At the Google. They wrote a very influential paper called "Attention is All You Need." Okay, so transformer model is basically has a two components called the encoder and the decoder. Encoder has multiple units, right? Each unit calculates something called attention, which is basically the similarity of that word with respect to that sentence, the importance of that word with respect to that sentence we are talking about, and it creates in multiple steps. So it encodes this information in multiple steps, and on the decoder side, we will have exactly the similar number of steps, and we try to decode it from that representation. That was something called a transformer paper. And this attention, you will see that this attention mechanism is used in almost almost any deep learning model, because that is so powerful concept. So BERT model exploited this attention mechanism and create a bidirectional transformer for distributed representation. The way they did it is they use something called a mass language model. So what it does is it takes when each sentence, it randomly masks the word in the sentence and then train the model to predict them. Okay, masking means that model, since the BERT is bidirectional, it looks from left to right as well as right to left. When you have a sentence, it looks from first word to the last as well as last word to the word to the first as well. So both directions. So given a masked word, it looks from both directions. Hence, it uses the full context of the sentence. Okay, both left and right surroundings to predict the masked word. So when you have a corpus, which is a huge corpus which you extracted from the web, English, let's say in this case, and then for each sentence, you randomly mask a word and then train the model to predict that. You continuously iterate over it. Okay, so randomly mask 15% of the words in the input, replacing that word with the mask token, a token like this, and you run the entire sequence through the birth attention based encoder, and then the decoder's job is to predict, decode it correctly and predict the mask word, and if it's correctly predicted, it is good. If it is wrongly predicted, you compute the error and adjust the weights. So the model only tries to predict the mask when the mask token is present in the input. It also has another one to train, is can we predict the next sentence prediction. So a pre-trained model with this kind of training will be quite useful in the question answering or other kind of natural language processing. Okay. So during training, the model gets input pairs of sentences and it learns to predict if the second sentence is the next sentence in the original text as well. So for training, it takes 50%, it will take a 2 pairs, 50% is correct, and the next 50%, it get a random sentence from the corpus, not the right one. So we force the model to predict it correctly. Through that, we adjust the representation. There's the 2 tasks it used, and through that, they created 4 different models. So one is BERT-based model, which is usually 12 layers with just 110 million parameters, which is a much smaller representation. Okay, BERT-based was trained on 4 cloud TPUs for 4 days, right? Whereas BERT-large is a 24 layer, which is double, and then it is trained on a 16 TPUs for 6 days. And each of these models has a case and case versions as well. Now, okay, so far I was now talking here is, initially I kind of briefly go through the core components of the neural models from a conceptual way. Then I looked into the distributed representation. I introduced the word to web, and then I looked into the one of the state of the art BERT representation, which Google created. That BERT models, like I said here, we could use any of this, which is trained. We could use this for another task, like a question answering. We can train a new system using this knowledge, word representation. We can create our own question answer for maybe, for example, in another language. Okay, so we can train this model for a downstream applications. What I'm going to discuss now is so these technology, how do we exploit for something called a downstream task like emotion detection, distributional representation, or a word embedding, can be used for something called emotion detection from short text. So what is a short text? Like a tweet, like a social media, right? So this is this first tweet from Al Jazeera, I think, says several people were arrested in the UK for protesting King Charles, including a woman charged for breach of the peace for sign saying abolish monarchy. And it says the royal cost taxpayers 100 million a year. Charles inherits the Queen 500 million fortune without paying inheritance tax. Okay, so that is a tweet that's known as a short text. Or if you go and look into another one, Tony Russell Rose, he was talking about some kind of summer school or something. Great to see so many talented individuals at the Goldsmith University London conference last week, user interface conference. Goodbye and good luck to our outgoing MSc cohort. I am sure you will go on to achieve great things. Right? And if you go and look at another one, after 4 years spent in Eureka News, first year as a PhD student, and then as a research scientist, I am thrilled to announce that I am going to join Spotify. Now, if you look at this short text, what kind of emotion expressed in it? You may ask the question, why do we need to learn the emotion from this text? So if you know that, in short text, and tweets, etc., we could detect events. Then we can understand that emotions expressed towards those events, in those events. then that will leave us to make a better decisions with respect to that events. So, for example, if there is a lot of anxiety or fear, then maybe that's an accident, right? Or if somebody talk about very happy things, it may be showing the mood of people in a place or an area, etc. So emotion detection from short text is an important field. However, these short texts are reasonably well written, but most cases it is unambiguous. It's very ambiguous, not unambiguous, ambiguous, or there will be a lot of errors, spelling errors, and also it lacks a lot of contextual data. So it may not be as long as this as well. It may not be as well composed as well. So extracting emotion from short text is a challenging problem. The question now is, can we build a deep learning model which can extract this emotion? So when you look at emotion, there is a two components, sentiment and emotion. When you talk about sentiment, we are talking about, you're looking at the polarity, right? Whether a sentiment is positive or negative. So let's look at the two other short texts. Like in this here, somebody said, huge congratulations to team Sigmoid, who smashed their fundraising target for the London to Brighton ride on Sunday. You are all amazing and thank you so much. So obviously this is a kind of positive or the positive polarity. There is another one, again I picked up from internet, Twitter. Deadly accident on Northern Bypass. Muswani motorcade knocks dead a Boda rider carrying 2 passengers. And so obviously this is an accident, 2 people dying. And so it's a negative sentiment, right? Whereas emotion detection, I try to do the much more fine-tuned work. So instead of this positive or negative, try to identify anger, disgust, fear, happiness, sadness, or surprise. So now these particular words, where are they coming from? They are coming from Paul Ekman's universal emotion model. Right, this is very influential paper, Paul Ekman, Basic Emotions, written in 1999. There he came up with 6 emotions, which he said is the most basic components: anger, disgust, fear, happiness, sadness, and surprise. So this is a 6-dimensional representation. There are other 4-dimensional representation or a 22 representation. There are multiple emotion models, but for our discussion we are going to focus on this. Whether we want to look into whether we can detect emotion from short text. Okay, our hypothesis is that sentiment classification can achieve now 80 to 90% accuracy nowadays. So, and when we experimented with many state-of-the-art emotion detection models, we realized that emotion detection performance is roughly 60%, okay, or less. So now the question now is, can we exploit the sentiment classification, which seems to be very high effectiveness, and then can we use that to bootstrap the emotion detection? So we created a hierarchical representation, and also instead of Ekman's model, we are using an enhanced emotion model. The reason is, if you go and look into Ekman's emotion model, you get anger, disgust, fear, happiness, sadness, and surprise. There is only one positive, happiness. Maybe you could say surprise can be positive or negative. I am surprised, so it can be, when you say it is surprises can be positive, but it can be negative too. So it is ambiguous. So we try to change that, some additional ones like a love and thankfulness and happiness, right? So if you look at this, we have potentially 3 positive and 3 negative emotions. That's why it's an enhanced emotion representation, right? The understand. So we looked into the way of looking at hierarchically. So that means if you look at If you ignore all the classes, if you look at the two classes on the left and right, we are looking at whether it is positive or negative. And if you are using a good model, if you can get 80 plus accuracy, eventually our performance will be much better. That is the idea of looking at this. Now we need a deep learning architecture for that, right? So we created a hierarchical model. Now it's let me try to walk you through this, right? Our input text first go through an embedding layer. So you know that in the previous section, I talked about word embedding. So we could go and look into use each word replies with the corresponding embedding vector. So in the examples I have shown that embedding vector can then find similarity between words. So it is much more powerful. So we use that. So the input sentence, each word represented by corresponding embedding vectors. Then we could use in this particular example here, I use a bidirectional long and short term memory model, right? There are so that's another deep learning model which uses information forward information and backward information, and in that process it creates a hidden layers of representation. So once we have that, we looked at the hidden layer, right? This hidden layer is gone through a dense layer. So dense layer is each neuron in this dense layer will the dimension of it we decide. Each neuron in this dense layer take input from all the neurons in the previous layer. That's why dense layer. So we have two dense layers, and then the output of that go through a softmax layer. When it go through a softmax layer, you get a kind of probability between a value between 0 and 1. It's a probability representation. That is, we call the attention value for that particular word. Okay. Now, if you take all the words in that sentence, you could get each word representation, attention representation, you could get a matrix. Okay. So that is basically for each word in that you get a attention matrix, which all that representation is average. It further goes through another dense layer, then a sigmoid activation function and output. So this one, the central part of this, get an output which shows whether it is positive or negative. Okay. Now we could find a loss here. If our calculation is wrong, positive or negative, we train this model and adjust the weights. Now, however, we are not aiming to create just sentiments, positive or negative. We want to identify the emotions. So if it is a positive, if you go back here in the hierarchical representation, we could potentially have thankfulness and love. But we only looked into in the initial experiment, or when it is positive, we only looked into one component, happiness. That means if this model says it is positive, we could detect it as a happiness, right? If it is negative, it goes through another layer exactly like this. However, this layer basically looking at whether it is anger or fear or sadness. If not, if that is error, then we try to refine the weights here. Now, in another case, when we have all these balanced classes, we could train this third component for a positive emotion as well. So this is what we call a hierarchical model. Now, is it a model or an architecture? How did I decide there are two dense layers needed? How did I decide what is the dimension of these dense layers? How do I decide what is the softmax? Many of these things are decided empirically, right? So basically, we are trying to learn. You remember that in the first part I discussed, we are trying to learn a nonlinear function. So we are trying to learn a complex function, and this architecture or the different neural components we use in this architecture, we create them to the assumption that we are helping them this function to learn that complex pattern through some simple patterns. Okay, that's what we are trying to do through this architecture. Like I said, No, there is no guidance which one. This is through our experience, empirically, we create this architecture. And if you look at the many classification using deep learning models, you could see a more or less similar kind of components coming. Then we have potentially 2 or 3 losses. We try to reduce all these loss together, right? In that way, that way we try to optimize all these weights together so that overall loss will be much lesser. Now, how do we evaluate? We used 4 data sets. In our case, Cloudflower and Tech are manually annotated, which is a smaller. And then Wang and Wen dataset is a social media dataset, which has millions of items, right? It is quite standard to use 80% for training and 20% for testing. And you run this for average 10 runs, cross-validation, and take the average results. We use, in common for classification tasks like this, we try to find accuracy, precision, recall, and F1 measures. Okay? So this is the hierarchical model, right? Here I give an example with the bidirectional LSTM, but I can replace this bidirectional LSTM with BERT model I discussed. BERT model has a distributed representation, and also the model architecture we can use for that representation we can use for classification. Similarly, another one called the gated recurrent unit bidirectional, we can use that. So that's why these are the state-of-the-art models are BERT by LSTM, which is called the SAVES in this case, and by GRU model. And the corresponding hierarchical version is the one we proposed. And if you look at the values here, you can realize that the corresponding the hierarchical model values are statistically significant when it compared to the baseline model or the base model we are comparing with. So, for example, if you take a BERT, hierarchical has an accuracy of 0.642, whereas BERT plain model has an accuracy of 0.535. And this is true. That difference you can see for all 4 data sets. So this basically shows how powerful the hierarchical model in detecting emotion from a short text. However, here in this particular case, we have only anger, fear, sadness, 3 negative emotions, 1 positive, right? But for the Wang and Wen datasets, which has much more additional data points available, so we decided to experiment with 3 positive classes and 2 positive classes as well, right? So if you look at the 3 positive, and we are in this case using only Wang and Wen dataset, we can see that accuracy still better for corresponding hierarchical models, and among them BERT model is much better, right? And however, you can know that the performance decrease when you compare 3-post model with the 2-post model, 2 positive model, or 1 positive model. The reason there is because what will happen is when you have multiple classes, positive or negative classes, this is a social media text, there is a potentially cross class talk between the training and data sets. That's why the overall performance slightly decreases. Okay, so the take home message here is, here we aim to solve the emotion detection problem on short text, but we also show that it's not that difficult to form some kind of research hypothesis and to create a new architecture and experiment for solving this problem as well, right? So in other words, if we do look at certain tasks, and if you look at this widely available distributed word representation, we can exploit for many different tasks, even using some kind of innovative architecture. Okay, So that problem can be a new problem, or the architecture can be something new, like a hierarchical architecture we are talking about. Okay. Now, what I will do is, that's one part of that idea of showing that. If you are interested, you could read that paper I mentioned there. Next one is, I want to look into something like an alternate, a different problem, which is a component of time series and the classification component, right? Horse race. This is an exploration. We haven't got any publications yet, but I will walk you through, the way we were doing it, so you get an idea, how to exploit deep learning for complex tasks like this. So horse racing, in the Western world, which is a lot of people bet for horse racing or a football, or predicting the outcome of football games, or they invest in a stock market. They want to know whether a particular stock is going to increase or decrease. So if you Betfair is one of the online systems platform where you can go on and bet. So here, this is not horse racing. This is football. You could see this Chelsea and Manchester City, etc. You could get for each game, your backing, whether they're going to win, and the odds values are given, and also corresponding values in those for those bets. Okay, and you can get this value for every 10 seconds, etc. This is keep updating the systems, and we can extract that. So effectively, you can get a time series data, right? You can get that for, I think it is for 2 hours before the game, roughly, like. Right? So that means this is known as technical data or odds data. But there, in addition, you could create fundamental data. You could go and look into the football team, the players, their previous performance, who is the manager, who is what kind of performance they had in the previous games, etc. Right? And that is we call that fundamental data. So similar data available for horse racing. So that's we get here, instead of football game, we get for each race, for each of the horses, corresponding odd value, and then you also get how much volume in that, how much money is available. So we can get a time series data for 2 hours of odds, as well as we can get a fundamental data: horse name, age, sex, weight, and also who is a jockey, who is a trainer, and how was their performance in the past games, etc. Around 400 plus features, right? So you get 2 different kind of data. How could we predict which will be a potential winner? So we created it's a very complex data set. We created an architecture for training a deep learning model, so that for data processing, these are the various components, right? So all the data is in a CSV files, and we did some kind of data pre-processing, did some data cleansing, and the missing data is removed, and then we split the data into validation, training, validation, and test set. Okay, and also it will create tensors. So the tensors are the data input going into a deep learning system. Then we go and extract embeddings for some of the categorical data, and also we look into a set of models like LSTM, CNN, and MLP, multi-layer perceptrons, and the predict outcomes, and then tuning and evaluation, testing on the validation data, right? Now here, this diagram basically show how we processed data. Now we could create many different models, right? And what we use for this experiment: pandas library for processing and loading data, NumPy to read the multi-dimensional arrays from the raw data, NumPy, right, and the PyTorch version for design the models, and scikit-learn also to evaluate the model and the cross-validate, and matplotlib to for the visualization, right? So these are all available, and we use the Google Colab to do the experiments, right? The data files were quite large in our case. It varies from 5 GB to 10 GB approximately, with the hundreds of columns, okay, of data. It's a huge data file. Now, we explored, I said there are something called a fundamental data. Each fundamental data has categorical values and continuous values, so continuous features. So categorical one go through an embedding, and continuous features go through a batch normalization, and they are concatenated, right? So we get a final representation. Then we create a, remember that I said attention is an important component. Each how important each component is, we can use an attention mechanism, and then in addition we will have multiple layers of dense and dropout layers, or softmax functions, and the prediction finally. This is something called, we call this we use that for the fundamental. Now we have a humongous data sets of time series data. The performance, the variation, the odds values, every in our case, what we have in every minute or every 30 seconds, and that's a huge data. So therefore, that we used a different architecture. Here we created tensor. It went through dense layers, and we reshaped that. Then we use a level of convolution, average pooling, etc. This is the architectural decisions, and then it went through an attention, finally a prediction, right? So we get a fundamental data, and we can predict which odds to win. We can also look at how people are putting the odds, how the odds value changing. We could use that as well, and then we can combine these two. This is the final model, a hybrid model, whereas we have used the one part for fundamental data, more like this, and another part for the technical data, and whether we could combine them and see whether we can predict a winning horse or not. Okay, and these are the kind of results we get for the validations by data test set, and on the right, only on the fundamental data, right? Like I said, the values here, particularly when you look at this CNN, we are getting up to 92%. Obviously, you don't never get that level of values. Later we realized in this particular experiment we had some corruption, data corruption. That is why that value. However, in the further experiments, we got an accuracy about 35% in predicting the winning horse. The kind of baseline our collaborators in industry use is a logistic regression, which can get up to 30-32%. So with the 35% of accuracy, we could get an improved return in value for 5 to 10%. Okay. Again, here, this is not a solved problem. This is an explored problem. You could see that how we can exploit deep learning architecture creatively for combining and predicting, combining different source of data and predicting an output. So maybe I don't think I have time to go through the recommendation model we did. I may stop here, and if you have any questions, or if you want to discuss anything, we could discuss now. Okay, Santosh, what do you think?
Yeah, I think we are actually having a little bit time for discussion.
Right. Okay.
Yeah, so I think so audience, kindly ask any questions if you have, or any clarifications if you wanted to do. Please go ahead by straight away unmuting your mic and asking the question to the professor, or you just type it on the chat box so that I can read it for the professor. So maybe if somebody before somebody comes up, just can I just ask some question regarding the last
Yeah,
slides that you
yeah,
have? Yeah,
right.
actually, you were trying to see how combination of different deep learning architectures will be useful for complex tasks like this. Is that was the aim actually, or
Now, actually, it's not to create that a complex architecture, right? So,
mhm,
in industry, right? Industry is the betting houses, the betting companies, right? So the individuals betting as well as big consortium, they also put millions of pounds, okay, for betting, right?
okay.
Now, when you look at a horse, 2 hours before you get something called as starting odds. That is the best odds you can get, right?
Mhm.
If you have a kind of a feel about which horse is going to win, you could bet a good amount of money, and if you're winning that horse win, you get a better return, right?
Yeah.
Now, so that's basically the first stage. That's what we will be using. This the first part of this fundamental data, where we look at the horses' performances, jockey, trainer, on the you name it, all sort of things, and then now that's the first stage, right? Now, if you have £1,000 you are betting, what proportion of that value you put it there, right? That's what the question the investor will ask you.
Yeah.
Then let's say 2 hours onwards and people started betting. Based on the people betting, the odds get refined by the betting houses because they don't want to lose money, right? So
Yeah.
they try to it's like a supply and demand. Odds get updated, right? If a lot of people are going to bet for a horse, then the odds started reducing, things like that, okay.
Yeah.
So that is a kind of time series problem, right? You can see
Yes.
that
Yeah.
the odds increase, decrease, etc. Maybe you could use that data and make an additional bet. You may want to lay some bets and go and say, at this point, I may bet on another horse in case my first bet is not returning. At least this will help me to recoup some of my losses, right?
Yeah. Yeah.
And if it comes to, let's say, you can bet at the last moment before the race starts, right? And then at that point, you put your bet in the betting platforms, right? So
Yeah.
another place you could update your bet as well. So you are so the problem is far too complex, even more complex than even stock prediction, because this horse. I mean, there is a no, there is no horse continuously winning in all this, right? So even
Mhm.
in the best performing horses, winning is maybe up to up to very small percentages in a certain races. So that means you need to bet at various points to have a better return. So that's the aim here, right? So
Yes.
that's why we look at different types of data and to how to combine them, right?
Yeah.
Now, this we haven't reached. I mean, I put this data, I put this work purposefully to show that how do we explore a space like this,
Yeah.
and we can now look at building a much better model, combining this and making predictions. You may want to ask the question: your investor gave you 1 million, how you are going to distribute that for this game, that money,
Yeah.
uh, and get a better return.
Yes. Yeah. Yeah. So, is it an online kind of model? I mean, we can update the model as we go ahead, or
I think model should be a training the model. So it's not the online model you're talking about, reinforcement learning based models. It's not like that.
okay.
So here we are training the model. In this particular case, we were aiming to predict whether a horse is winning or not, right?
Yeah.
But there are many things you could do. We could look into the rank order of the horses, or you could look at when you have £1,000 or ₹1,000 or a ₹10,000 or a lakh of rupees, how you are going to distribute your bets so that you will have better value for money, better return.
Yes. Yeah.
And
Yes.
I am only scratching the surface here.
Yeah, yeah,
You know, so that is exactly like this, right? Now, how do we formulate the problem? How do we exploit the data in what combination?
yeah.
And you can see it's a space and time is involved
Yes,
here, yeah.
yes, yes, yeah.
So yeah,
Yeah, so that tensor becomes the natural kind of
correct.
an object, yeah,
Yeah,
for the input.
yeah. But then the question is, how do we make the decisions
Yeah, yeah,
at various points, or how do the model tell us? Okay, this pattern I have seen. Maybe you should lay your bed and go and see whether you can get something returned. Things like
yeah,
that.
yeah, yeah. So it should imbibe all the complexities of a betting kind of a scenario, right?
Yeah. In real life, they
Yeah.
all these betting consortiums, they
Mhm.
do automatic systems, right? And they
Yeah, yeah,
use like a simple machine learning models. And I personally think there's quite large amount of research can be done here.
yes,
Uh,
yes, yeah. Very, very interesting work. I think a lot of things to be done in terms of, yeah, yeah. So, audience, please, if you have any questions, please ask. So we can wind up in 10 minutes.
Okay, Professor Joemon, it was a very interesting session, good tutorial. So I just want to pose two questions. One
okay.
is regarding the spellings. So spellings changes the words or word meanings. So how you accommodate that? That is one thing. And second is regarding the results that you have shown. So see, you have shown the results of your horse race experiment and all with accuracy 35%, and so on. So in academic research, we do this kind of works, and we would like to send it to some journals.
Correct.
So will these journal people appreciate that kind of results? In actually, there may be when we process the text, there may be one problem. So maybe we will have to apply some prediction to find out a journal with low accurate results that we get out of actual
Okay. Yeah,
experimentation. So
yeah.
how you do
So,
that?
so I think let me try to answer the second question first, right? So the second question is the metrics I show here. Will they lead to any publication, right? Is that kind of correct, Samu? Philip? Yeah, Philip?
Yes, 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 yes.
Yeah.
Please,
So,
yes, yes.
so answer there is, right, when you look at a model like this, right, if you can show some innovation, novelty, right, and if there is a novelty, and then you can compare with other state of the arts and show that it improves, yes, it can be published. Okay. In that case, in this particular problem, you will be looking at something uh, innovatively on that problem uh, in solving that. Okay. So yes, we can get that if there is an innovation in our architecture, in our approach, etc., and we can justify that. It is also the case that, like you said, you may need to show, like when you predict these horses, can we convert that into some kind of called some kind of monetary return, right? Whether you can get that, you could show that it's called something called the Kelly's wagering, etc. is used in the betting field. How do you distribute your resources and get the best values? You can show that. That will be even better. Okay. But it's important. There are novelty come from two different parts. One is the application. Second one from the architecture or the model, what you call here. Okay. Did I answer your question?
Okay, okay. What about the other question
Yeah.
regarding spellings? Yeah.
The spellings, right? So if you were to look into the birth, right, it is created from the World Wide Web. The documents, nobody created this. It's all multiple people creating. Obviously, when you extract things like from the web, there will be mistakes, right? Now, you take the word, one word, and if there is only one spelling mistake, you are only looking at the statistics. How often these terms co-occur in text. You see that window sizes we discussed. Let me try to. Okay. Yeah, here, right? This is the sampling happening on the text, right? And what will happen is you are looking at the potential of that word's co-occurrence information from the corpus. So suppose the spelling variation of a word occurs many times, then there will be much similarity between them. But it is only happening once, then effectively that will be too different. You are not looking into any other kind of similarity. You are only looking at, in developing these models, you are only looking at the probabilities or the real life occurrence of these terms in the corpus. Okay, so it is possible for a word there is a misspelled word and it only occurred once, they will be considered as two different words. Whereas such spelling variations occurred many different ways. So, for example, American spelling and British spelling, like for modeling, MODELLING in British and symbol 1LING American. So you would expect many of them occurring. So in that case, the similarity will be higher for those words. Yeah,
Okay, thank you. Thank you.
Thank you.
Yeah, if you have no more questions, maybe let me try to wind up and summarize the talk by Professor Joemon. So Joemon started with very basics of deep learning, starting from the neurons. He discussed what is a feedforward network. Along with, he discussed what is linear separability, why it is important, and how the architectures are learning from the errors it makes, and how the backpropagation accommodates that, and what is the importance of the gradient descent algorithm. Then he summarized learning as learning simple structures in the form of functions to form complex representations or complex structures. And he stressed the importance of representation learning and the importance of depth and width of the architecture. So we can design deep learning architectures and make something out of that. And parallelly discussed what is the difference between the machine learning approach and deep learning approach in terms of the machine learning concentrates the feature, maybe it starts from learning features, or feature learning is the, or it learns from the features, and deep learning itself creates the features for itself for the learning. Then word embedding was discussed in very detail. Word to vec, two types of representations, continuous bag of words and skipgram. I think he has discussed in detail with examples. Then it was extended to the sentences and paragraphs, and directly he introduced Google's most famous work on bidirectional encoded representation from transformers, and attention is most important, and it was the best paper maybe I can highlight, which Joemon was mentioning. Then after discussion of all these basics required to understand what basically deep learning does, he jumped into problems especially two problems, one with emotion detection and another with very interesting problem, time series and kind of classification using the horse racing kind of a problem. So in emotion detection, how the hierarchical representation basically used and how the models are evaluated was explained by him, and finally the time series related problem. It's a new kind of a problem. I think a lot of work to be done on this area, but it's a very interesting problem. Thank you for introducing that to us. So in short, he was directly exploring the possibilities of deep learning in different kind of problems. I think we should all join together to thank Professor Joemon for his time to discuss the basics as well as how these applications using deep learning can be built from the scratch. I think all the details were discussed within this given time frame. It was excellent, sir. We, on behalf of all the audience and the faculty members of Department of Computer Science, Cochin University, we are very thankful to you, sir. I think we will collaborate soon with the department, and we await for your kindness to offer your wholehearted support to our department. Thank you so much for your willingness to come and spend your valuable time with us, sir. Thank you so much.
Thank you all. Thank you for this opportunity. You know, Cochin University is my alma mater as well. So
Yeah.
each time when I come back, you know, it's very exciting for me too. Now, all the best. Okay.
Yeah. Thank you so much, sir. Good night. So, dear participants, so we have the last end of this session. Thank you for your time, and kindly join us tomorrow sharply at 7. We will be starting with another exciting lecture from a very learned person. Thank you so much. Good night and have a nice time ahead. Thank you.